Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the effects of bank pressure. Converging or converging diverging nozzles are found in many engineering applications, including steam and gas turbines, aircraft and spacecraft propulsion systems, and even industrial blasting nozzles and torch nozzles. The exit velocity, the mass flow rate, and the pressure distribution along the nozzle are affected by the bank pressure. Let's check the effect of bank pressure on the pressure distribution along a converging nozzle. Cases 1, 2, 3, 4, and 5 are for different bank pressures as shown in the figure. Consider the subsonic flow through a converging nozzle as shown in figure 9.8. The nozzle in it is attached to a reservoir and pressure PR and temperature TR. The reservoir is sufficiently large so that the nozzle inlet velocity is negligible. Since the flow velocity in the reservoir is zero and the flow through the nozzle is approximated as isentropic, the stagnation pressure and stagnation temperature of the fluid and any cross-section through the nozzle are equal to the reservoir pressure and temperature respectively. Now we begin to reduce the bank pressure and observe the resulting effects on the pressure distribution along the length of the nozzle, as shown in the figure. If the bank pressure PB is equal to P1, which is equal to PR, there is no flow and the pressure distribution is uniform along the nozzle. When the bank pressure is reduced to P2, the exit plane pressure PE also drops to P2. This causes the pressure along the nozzle to decrease in the flow direction. When the bank pressure is reduced to P3, the mass flow reaches a maximum value and the flow is said to be choked. Further reduction of the bank pressure to level P4 or below does not result in additional changes in the pressure distribution or anything else along the nozzle length. The nozzle exit pressure PE is a plot of QM versus P2 over P asterisk for a converging nozzle is shown in figure line 6. Notice that the mass flow rate increases with the decreasing of pressure ratio P2 over P asterisk, reaches a maximum at P2 equals Pc, and remains constant for the pressure values less than this critical ratio. Also illustrated on this figure is the effect of bank pressure on the nozzle exit pressure PE. To summarize, for all bank pressures lower than the critical pressure Pc, the pressure at the exit plane of the converging nozzle PE is equal to Pc. The Mach number at the exit plane is unity, and the mass flow rate is the maximum flow rate. Because the velocity of the flow is sonic into the throat for the maximum flow rate, a bank pressure lower than the critical pressure cannot be sensed in the ladle upstream flow and does not affect the flow rate. Consider the converging-diverging ladle shown in Figure 9.9. A fluid enters the ladle with a low velocity and stagnation pressure P asterisk. Now, let's talk about the following cases. Let's look at case A, where we have pressure balanced, that is, PB equals P asterisk. There is no flow through the ladle. This is expected since the flow in a ladle is driven by the pressure difference between the ladle inlet and the exit. Now, let's examine what happens as the bank pressure is lowered. Firstly, let's look at case B, where we have lowered bank pressure PB. The flow remains subsonic throughout the ladle, and the mass flow is less than that for choked flow. The fluid velocity increases in the first section and reaches a maximum at the throat. However, most of the gain in velocity is lost in the second section of the ladle, which acts as a diffuser. The pressure decreases in the converging section, reaches a minimum at the throat, and increases at the expense of velocity in the diverging section. Let's examine what happens as the bank pressure is lowered further from that of case B. Now, let's look at case C, where we have lowered bank pressure PB equals PC as shown in the figure. The throat pressure becomes PC and the fluid achieves sonic velocity at the throat, but the diverging section of the ladle still acts as a diffuser, slowing the fluid to subsonic velocities. The mass flow rate that was increasing with decreasing PB also reaches its maximum value. Recall that PC is the lowest pressure that can be obtained at the throat, and the sonic velocity is the highest velocity that can be achieved with a converging ladle. Thus, lowering PB further has no influence on the fluid flow in the converging part of the ladle or the mass flow rate through the ladle. However, it does influence the character of the flow in the diverging section. Now, let's look at case D, where we have lowered bank pressure PB. The fluid that achieved a sonic velocity at the throat continues accelerating to supersonic velocities in the diverging section as the pressure decreases. This acceleration comes to a sudden stop, however, as a normal shock develops at a section between the throat and the exit plane, which causes a sudden drop in velocity to subsonic levels and a sudden increase in pressure. The fluid then continues to decelerate further in the remaining part of the converging-diverging ladle. Flow through the shock is highly irreversible, and thus it cannot be approximated as isentropic. The normal shock moves downstream away from the throat as Pb is decreased, and it approaches the ladle's exit plane as Pb approaches Pe. When Pb equals Pe, the normal shock forms at the exit plane of the ladle. The flow is supersonic through the entire diverging section in this case, and it can be approximated as isentropic. However, the fluid velocity drops to subsonic levels just before leaving the ladle as it crosses the normal shock. Now, let's talk about this case, that is, the bank pressure is lower than Pe. The flow in the diverging section is supersonic, and the fluid expands to Pf at the ladle exit with no normal shock forming within the ladle. Thus, the flow through the ladle can be approximated as isentropic. When Pb equals Pf, no shocks occur within or outside the ladle. When Pb is less than Pf, irreversible mixing and expansion waves occur downstream of the exit plane of the ladle. When Pb is larger than Pf, however, the pressure of the fluid increases from Pf to Pb irreversibly in the wake of the ladle exit, creating what are called oblique shocks. Okay, that's all for this task. Thank you very much, and see you next time.